Everyone, so the question we're looking at is question number 1 of summer 2008 paper 49702. Question number 1 is define the radian. Pretty straightforward. You just need to write it is defined as an angle subtended at the center of the circle. You will get 1 mark for this when arc length is equals to radius. You will get the second mark for this. Then moving on towards the second part, that says a small mass is attached to a string. The mass is rotating about a fixed point P at a constant speed as shown in figure 1.1. Explain what is meant by the angular speed about point P of the mass. Now, there's a catch. If I were to just simply write the definition I've learned for angular speed, that is, it is the rate of change of angular displacement. It is the rate of change of angular displacement. If I were to just write this, I will get 1 mark. The reason why this is for 2 marks is because this question right here is case specific. Let me write this in red. It in red. This is a case specific question. What we mean by that? The reason why they have given us such a big story above, that it's rotating about a point P, is so that we can relate our definition to this example, to this question given to us. So I can say it is a rate of change of angular displacement about point P. This, or you can just say it is the rate of change of angular displacement by the string. Better way is to write by the string. Moving on towards the B part. A horizontal flat plate is free to rotate about a vertical axis through its center as shown in figure 1.2. A small mass m is placed on the plate at distance d. Distance d is the radius from the axis of rotation. The speed of rotation of the plate is gradually increased from 0 until the mass is seen to slide up the plate. The maximum frictional force F between the plate and the mass is given by the expression F is equals to 0.72 W, where W is the weight of the mass m. The distance d is 35 centimeters. Determine the maximum number of revolutions of the plate per minute for the mass m to remain on the plate. Explain your working. Okay. Point number 1 that we need to understand is that this frictional force right here is providing us with the centripetal force. Centripetal force itself is not a force, not a concrete force. It's just a resultant force. So I can say there are 3 formulas for force that we have read in circular motion. That is, F is equals to mr omega square. I'll just write them down and we'll pick the best one that fits here. F is equals to mr omega square. F is equals to mv omega, and you have F is equals to mv square divided by r. Now they have given us r, but we do not know what v is. So the best thing that you can do is that we go for this formula. F is equals to mr omega square. Why? Because maximum number number here means omega, frequency, and we know we can find frequency once we find omega, because omega is equals to 2 pi f. So first we'll use this formula. We know this centripetal force is equals to this frictional force, so we will write 0.72 W, which is the weight, which is equals to mg, is equals to m into r, which is given to us as 35 centimeter, which we will convert to 0.35 into omega square, which we have to find. I can just cut this m out because we do not know what m is, and then now when we plug these values in, you have 0.72 into 9.81 is equals to 0.35 into omega square. When you plug this in your calculator, you have 0.72 into 9.81 divided by 0.35. You get omega as 4.49. Now, omega is rad per second. Now I know omega is equals to 2 pi f, 2 into pi into f. I have to find f because f is the number. So when I divide 4.49 divided by 2 pi, I get 0.715. When you get 0.715, I need to multiply this with 60 so that I can get it into per minute, because this is per second. So I have to multiply this with 60, so you get 42.8, which you can write as 43, and so your final answer is 43 per minute. 43 per minute. Now the C part. The plate in B is covered when stationary with mud. Suggest and explain whether mud near the edge of the plate or near the center will first leave the plate as the angular speed of the plate is slowly increased. Now, we know if I were to go back here and visualize this, I place mud here, and we can call this distance r, and then you have mud here and we call this distance t. We know if you look at these formulas for f here, you can see in all of them, in this especially which we used, as r increases, f also increases, the centripetal force also increases. So the force that's keeping this mud on the disc, on this plate, is the frictional force. And we know frictional force is providing the centripetal force. So when the radius increases, as the radius increases, the centripetal force, which is the frictional force, because frictional force is providing centripetal force, as the radius increases, the centripetal force required to keep the mud on the plate also increases. So the requirement of the centripetal force as the radius increases also increases. So it has to, like, centripetal force has to, like, keep on increasing and increasing so that it can keep the mud on the plate. So as a result, it cannot keep on increasing. So at a certain point, the mud at the edge will be the first to leave the say, because the one that's near the center, that requires very less centripetal force, very less frictional force to keep it there. But as the radius increases, more and more frictional force is required, and it cannot keep on increasing, keep on meeting its requirements. So it will be the first one.